Hi all, let's take a look at your practice test covering sections from Chapter 8 and Chapter 10 up through 10.6. Your first problem is going to be different from problems 2 through 12. So first problem you'll need to remember is on sequences, not series. They follow different rules. Problems 2 through 12 will be our Chapter 10.2 through 10.6 sequences problems, and then the last two problems go back to Chapter 8 where you're asked a question on arc length and a question on surface area. So first of all, keep in mind that I will allow you to use any one page of notes, and keep in mind that is one-sided page of notes, so you can write down whatever you want on any one standard sheet of paper. So it has to be the same size as a normal piece of paper. So anything like that you can fit on one page, whatever you think would best help you on the test, you're welcome to bring. For this first question that's with our sequences, the way we know a sequence converges is if we can take the limit of the general term of the sequence, and if that limit goes to any finite value, then the sequence converges. If it doesn't, if it goes to infinity, or if it goes to some undefined value where it's not going to any one value, then it diverges. So in the first problem here, I gave you the general term a sub n is equal to n times the group, the square root of n squared plus 3 minus n. Now, this one's a little tricky when you think about it. If you just say, well, if I allow n to go to infinity, I would have an infinite term times this would be a term approaching 0, because you'd have a term approaching infinity minus a term approaching infinity. So I'd say, well, that's indeterminate. So what I did, I first algebraically simplified, which I strongly recommend there, and say, well, please notice if I ask you to factor a factor of n out of this group, the second term has an n. You can factor an n out of the square root by saying a factor of the square root of n squared out. When you factor an n squared out of your square root, your first term becomes 1. Your second term becomes 3 over n squared. So I factored that n out of this term, the square root of n squared out of this term, bring that to the outside, and it makes your n on the outside an n squared. Now, this is still indeterminate, because you're going to say, well, this term's going to go to infinity as n goes to infinity. This term as n goes to infinity would become the square root of 1 minus 1, which is also 0. Infinity times 0 is one of our indeterminate forms. So here's what I did. I said, well, anytime I have an indeterminate limit, I should be able to use L'Hopital to figure that out. In order to use L'Hopital, I have to get a fraction. So this goes back to section 4.5 in your book, back to the good old Calc 1 skills. So what I did in this case is I said this limit as n approaches infinity of the general term a sub n, that's going to equal the limit as n approaches infinity, and I've left all of this in the numerator. If I need to force that n squared down to the denominator, you need to put it as n to the negative 2, or as I did here, 1 over n squared, same thing as n to the negative 2. Now, L'Hopital tells us to take the derivative of the numerator and the derivative of the denominator, and then try to take the limit. Because at this point, this fraction is of indeterminate form. The numerator is going to 0, the denominator is going to 0 as n goes to infinity. 0 over 0 is indeterminate in limit form. So I can say, well, okay, take the derivative of the numerator. This group is the same thing as the group to the 1/2 power. I bring the 1/2 down in front, times the group left alone to the negative 1/2 power, times the derivative of the inside. Derivative of the inside is the same thing as the derivative of 3n to the negative 2 with respect to n. So I just said, well, that's going to be negative 6n to the negative 3. I'm looking at my denominator and I'm thinking of it as just n to the negative 2. So its derivative is going to be negative 2n to the negative 3, which is where I get that. Then a lot of stuff's going to cancel here. Notice Your factor of n to the -3 in the numerator and denominator cancel. 1/2 times -6 would be -3, but I see that my denominator is -2, so I just went ahead and canceled the negative out. That's where the 3 came from. And then I can say this group really is a 1/2 power in the denominator. And if it goes to the denominator, it becomes positive, and I went ahead and put it as the square root. Then I had the factor of 2 left in the denominator as well. So I ended up with the limit as n approaches infinity of 3/2 on the square root of 1 plus 3/n squared. Then as n goes to infinity, I know that term goes to 0. That's okay. I still have 3/2 on the square root of 1. And so I can say, if I take my limit as n approaches infinity, my final answer is just 3/2. Now, remember what I said earlier. If this were a series, this would be evidence that the series does not converge. But in a sequence, we say a sequence converges anytime the limiting value goes to any finite number. We can say sequence a sub n converges to 3/2. Again, if it were a series, it would diverge because the limiting value is not 0. So I can say, all right, this sequence converges to 3/2. Now, what about the second part of this question, part B? I give you the sequence b sub n, and I just define it to be the exponential function e to the 4 minus n squared. So right now, if I'm thinking, all right, if I allow n to go to infinity, that's going to be e to a negative infinite power, which you might understand is 0, and you know it converges from that. Just to make sure I was very clear, I went ahead and rewrote this, and I said, well, the limit as n approaches infinity of this exponential function. I can say I could put that exponential function in the denominator if I change the sign on the exponent. That means e in the denominator would be to the positive n squared minus 4 power. Now, this makes it a little bit more obvious. When n goes to infinity now, you're going to have e to an infinite power, which definitely is infinity, but your numerator is just a 1. 1 divided by an infinite number, or 1 or any finite number divided by an infinite numbers, has a limiting value of 0. So therefore, we can say this sequence b sub n converges to 0. Now, our first of the series questions, number 2, asks you to find the sum of the series from 3 to infinity of 1 over n minus 1 times n plus 1. So I can say, well, okay, that's a telescoping series. Instantly, you should think back to your wonderful method of partial fraction decomposition and say, it's the same idea as far as how I begin the problem. I look at my fraction within and I break it into a over n minus 1 plus b over n plus 1. When I multiply by the least common denominator of n minus 1, n plus 1, I'm left with 1 is equal to a times n plus 1 plus b times n minus 1. Then I'm able to allow n to equal 1. That cancels out my b term. And I'm left with the equation 1 is equal to 2a. Thus, a is equal to 1/2. If I allow n to equal -1, that results in the equation -2b is 1. Thus, b is -1/2. Now, if you put that 1/2 in for a and the -1/2 in for b, you see that this is the summation of 1/2 over n minus 1, and then it would be plus a -1/2 over n plus 1. Instead of writing it like that, I thought it would be better to go ahead and factor that 1/2 on the outside of the summation. So you'll say, so you'll see I put our original summation is equal to 1/2 times the sum from 3 to infinity of 1 over n minus 1 minus 1 over n plus 1. Now, once I do that, we know we're trying to find the sum of the series. The sum of any infinite series we can call S. So I'm saying S is equal to 1/2 times the limit as n approaches infinity. And then you just need to start thinking about what the terms would be. Your first term is when n is 3. So plug a 3 in. You'd get 1 over 3 minus 1. That's where the 1/2 came from. Minus 1 over 3 plus 1. Well, that's 1 over 2 minus 1 over 4. And at the beginning, I did not have those red slashes that came later. So the first term is 1/2 minus 1/4 plus the second term would be when n is 4. When you allow n to equal 4, you're going to have 1 over 3 minus 1 over 5. And then I quickly saw that each successive term thereafter is going to have the terms canceling out. And you think, well, why? Because the third term is going to start with n equals 5. When n is 5, your first term is a positive 1/4. Your second term is going to be a minus 1/6. That positive 1/4 cancels with 2 terms prior minus 1/4. And then I can see that, oh, okay, then every minus term is going to cancel out with the plus term 2 terms later on. My next term would start with a plus 1/5. That's going to cancel out this minus 1/5. The next term would start with a plus 1/6. That's going to cancel out this minus 1/6. So I see that every one of these terms are going to cancel with the exception of the first part of the first 2 terms. There's nothing that's going to cancel out the positive 1/2 or the positive 1/3. In the same manner, I can see that, well, this item by item cancellation is going to occur, except for the first part of the first 2 terms. And then logically, I can say, well, then the last part of the last 2 terms is not going to cancel either. So that's why I went ahead and said this keeps on going all the way to the n minus first term. N minus first term would be 1 over n minus 2 minus 1 over n. And then your last term, the nth term, which is just your 1 over n minus 1 minus 1 over n plus 1. I know that there's never going to be a positive term that's going to cancel out the minus 1 over n. Notice the greatest the positive term can get in the denominator is 1 over n minus 1. Can't cancel out that minus 1 over n. Also, nothing's going to cancel out the minus 1 over n plus 1. So I have 4 terms that did not cancel, the first part of the first 2 terms and the last part of the last 2 terms. The sum of this series is going to be 1/2, the limit as n approaches infinity, of the 4 terms that did not cancel out. Now, in all actuality, it's really irrelevant, those last 2 terms, because keep in mind, we're taking the limit as n approaches infinity. So as n approaches infinity, those last 2 terms go to 0. So the only thing I had to worry about was 1/2 plus 1/3. And I said, well, that's going to be 3 over 6 plus 2 over 6 is 5 over 6. I'm taking the sum of 5 over 6, multiplying it by 1/2. Please don't forget the 1/2 I had to factor out in the very beginning of the problem. My sum is going to be 1/2 times 5 over 6 for 5 over 12. Gorgeous problem there. The next 2 problems are pretty quick. They're both our geometric series. And we remember the geometric series test says that they converge anytime the common ratio r is a number less than 1. And that needs to make logical sense. You say, well, of course it's going to converge if r is less than 1. That's just guaranteeing that each term of your series is getting smaller in absolute value. And now the value of r, it could be negative. So I should say the absolute value of the common ratio needs to be less than 1. So positive or negative values between -1 and 1 will ensure that each value of your series is getting smaller as you go on to larger values of n. If it's equal to 1 or greater than 1, your series is going to diverge because you're adding a summation of numbers that never get smaller. Now, if I look at the first one, the mistake that I see students make on a problem like number 3 is they'll tell me that the common ratio is 3/4. That's terrible. So the common ratio is whatever value is raised to the n. So in this problem, you see, well, that 3 is not raised to the n power. So if the only term raised to the n power is the 4, but be careful, that's a 4 in the denominator. I need to understand that this could be rewritten as 3 times the group 1/4 to the n. So when I ask you what your first term is, remember C is always your first term. Your first term is just what happens when you plug the first term of your series in. You say, well, if I plug a 0 in for n, my first term would be 3 over 4 to the 0. That's 3 over 1. C, the first term is 3. The common ratio here, I need you to understand, is 1/4, because this is the same thing as 3 times 1/4 to the n power. And so my common ratio, each term is going to get smaller by a factor of 1/4 as we go. Since that 1/4 is less than 1, this series is clearly going to converge. And then I said, if it converges, find its convergent sum. The sum of any geometric series that converges should be the first term divided by 1 minus the common ratio. The first term, plug in 0, you get a 3. So C is equal to 3 over 1 minus R becomes 1 over 1 minus 1/4. In order to simplify that easily, just multiply by 4 over 4. That will give you 12 over 4 minus 1. That's 12 over 3. 12 over 3 is the final answer of 4. So if we add the terms in the series, if you just wanted to list out the first few terms, it'd be 3 and then 3/4 plus 3/16 plus 3 over 64. And it would keep on going like that. The sum of all of those numbers would approach 4. That's the limiting value. Now, for number 4, similar but more interesting problem, we have the summation from 0 to infinity of 7 plus 6 to the n divided by 7 to the n. Now, what's important here is that you understand this is not one geometric series, because there's 2 terms in that numerator. So just like we can split up an integral problem and say we can distribute the denominator into each term in the numerator and integrate 2 separate, easier problems, same thing in this. In a summation problem, I can say it's the summation from 0 to infinity of 7 over 7 to the n, plus the summation from 0 to infinity of 6 to the n over 7 to the n. That's what I've done here. And in each of these cases, I've rewritten it to make it a little easier to understand. So this first part, if I had 7 over 7 to the n, I can think of that as 7 times the common ratio 1/7 to the n power. This makes it very clear what my common ratio R is in this problem. R is going to be 1/7. Your first term is going to be 7. When you let n equal 0, you're going to have 7 times 1/7 to the 0. So you say, okay, the first term C is 7. Your common ratio is 1/7. I can find the sum of this series. Now the sum of the other series, you'd say it's plus the summation of 6 to the n over 7 to the n. Well, that's the same thing as 6/7 to the n. Here I can see my first term, C is going to be 1. If I let n equal 0, I would get a 1. And clearly my common ratio, each successive term after that, is going to be multiplied by an increasing power of 6/7, thus getting smaller and thus converging. That's what I said here. In your geometric series test, you need to make sure that both of these series converge, and clearly they do. Both of the R values have an absolute value less than 1. So the sum of this series is the sum of these 2 individual series. The first one is going to have the sum of the first term C, which is 7, divided by 1 minus the common ratio, 1 minus 1/7. Your second one, your first term would be 1, divide that by 1 minus R, where R is 6/7 here. In both of these, I just multiplied by 7 over 7. When you do that in your first one, you get 49 over 7 minus 1. In your second one, you'll get 7 over 7 minus 6. So clearly that gives me 49 over 6 plus 7. It's the same thing as 49 over 6 plus 42 over 6 for a total nice answer of 91 over 6. And I know what you're thinking. You're thinking that's a pretty cool problem. It is pretty cool. Let me go on to number 5. Number 5 says, use the test for divergence. So let me make sure I talk about this because I don't want the problem on the test to be slightly different. And then you're like, oh, I don't know what to do with that. The test for divergence, I need you to remember, it can only tell you if a series diverges. What does the test for divergence say? It says, well, if the limit of the term, of the general term, in this case, the general term as the variable k, I can say, well, the limit of a sub k as k goes to infinity, if that has a limiting value of 0, then the test for divergence tells us nothing. The series could converge, could diverge. Well, what if the limit as k approaches infinity of the general term in there gives us some value other than 0? the test for divergence says if it's anything other than zero, then that series diverges because you're adding an infinite number of non-zero terms. So you say, okay, if it's not zero, it diverges. If it is zero, we don't know. Test for divergence is inconclusive. Now, please keep that in mind. Now, on this test, I gave you a problem and I asked you to use the test for divergence. And so you say, all right, can I take the limiting value of the index value, k in this case, let that general term go to infinity? Is that going to equal zero? And if it is, then it's inconclusive. If it's not zero, then we say the divergence test tells us this series diverges. So I took the limiting value of a sub k in this case. So when I did that, I just went ahead and looked at, well, my value of my variable k in the numerator would be a k squared. In the denominator, I'm going to have a k to the third. Yes, I would have other terms of the polynomial in the numerator and denominator. Those terms are irrelevant. Please remember, in an infinite limit of a rational function, all you have to do is say, well, you only care about the largest powers in the numerator and denominator. And in this case, since the denominator is of greater power, this fraction is going to zero. So you say, okay, the limit as k approaches infinity of k squared over k cubed, it would reduce down to 1 over k. And then as k goes to infinity, that goes to zero. So we say, well, what does this tell us? It doesn't tell us anything. The test for divergence is inconclusive, but I want you to say something. So you say, well, all right, since the limiting value is zero, therefore, this series could converge or diverge. I don't want you going in and using any other test to tell me if it converges or diverges. We're just supposed to use the test for divergence. So use the test for divergence to determine if this series diverges. Well, the test for divergence doesn't tell us in this case. So the only time it tells us something is if this is some finite value other than zero. And in that case, it would tell us it diverges. In this case, it's saying, oh, it could diverge, but it could also converge. So divergence test doesn't help a lot in this problem, but that's okay. We still use the test for divergence. Number 6, we're supposed to use the comparison and p-series to determine the convergence of 1 over the cube root of n squared minus 5. So I'm thinking, okay, comparison and p-series. P-series is just 1 over n to a power, where the p-series power is always the degree difference between the numerator and denominator. So before I even do this problem, I'm thinking, well, the power on n in that denominator, that's essentially n to the 2 over 3 power. So I'm thinking, okay, I'm going to compare this with a p-series of 1 over n to the 2/3. That's a p-series of 2/3. What do I know about that? I know that it diverges. All p-series where p is less than or equal to 1 diverge. So that's telling me I need to show that this series diverges with the comparison test. That's how I did it. So I said, all right, here's my series. I'm going to compare it with a divergent p-series of 1 over n to the 2/3 power. And again, I know that that diverges because the p-series test is anytime p is less than or equal to 1, it is a divergent series because the fractions are not getting small enough quickly enough to converge. If that were any number greater than 1, like if that was 1 over n squared, converges. Now, the way I show that our series is divergent is I have to show that the general term of our series is greater than the general term of the corresponding p-series. And just to make sure I was very clear here, I went ahead and put the fractional exponent back in terms of radical form. And I said, well, n to the 2/3 power, that's the same thing as the cube root of n squared. Now, clearly, this fraction is larger than this fraction. You think, why is it clear? Well, think about it. You're subtracting something from that denominator. So I know that this denominator is always going to be smaller than this denominator. The same numerator divided by a smaller denominator makes this fraction larger than this fraction. So I say, okay, this is always going to be larger than this as n goes to infinity. So then that's showing that the general term of our series is larger than the general term of a series that diverges, which is conclusive evidence to say that our series in question also diverges. That is the the comparison and p-series test. Now, for number 7, I ask you to use the Leibniz test, also known as the alternating series test, to determine the convergence of the sum from 1 to infinity of -1 to the n over the square root of n. So whether you call it the Leibniz test or the alternating series test, you just say, all I have to do is take the limit of the non-alternating part, and if I can show that that limit goes to 0, boom, by the Leibniz alternating series test, this series converges. So here's my series. And I just said, well, the limit as n approaches infinity of the non-alternating part. So you just ignore that -1 to the n. The numerator is just going to be 1 over the square root of n. So if this did not alternating sign, this would be my general term. So does the limit as n approaches infinity of that term go to 0? Sure it does, because it'd be 1 over the square root of infinity. 1 divided by any form of infinity goes off to 0. Since that goes off to 0 by the alternating series test, again, or the Leibniz test, whatever you wanted to call it, we would say this is conclusive evidence that this series converges. What if that had been anything other than 0? Then you wouldn't be able to say it converges. But as long as you can show that's convergent, or sorry, as long as you can show that that is 0, you've shown that the series converges. Now, for number 8, I'm asking you to use the limit comparison test to determine the convergence of this series. Now, as soon as you see this series, anytime what's inside would be a rational function, you should be thinking, well, okay, I'm going to compare it with a p-series. P-series should always be the degree differential between the numerator and denominator. There's a degree difference of 2. I'm going to compare this with 1 over n squared. What do I know about 1 over n squared? It is a convergent p-series with p equals 2. Convergent p-series are always values of p where it's greater than 1. So you'll see as I work to my problem, here's the problem I'm trying to work with. I'm going to compare this with a convergent p-series, 1 over n squared. Converges because that degree on the n is 2, and anytime it's greater than 1, it converges. Now, what does the limit comparison test tell us? It tells us that we need to find the limit as n approaches infinity of the general term of the series we're trying to find something about, divided by the general term of the series we know the convergence of. And if this fraction is just some finite number, we can say, oh, then our series is just a constant multiple of the other series. So whatever the convergence divergence of the other series is the same as our series. So in this case, I was able to take this limiting value, and if I divide by 1 over n squared, that's the same thing as multiplying by n squared over 1. So you'll see that's why my numerator just became 3n cubed plus 7n squared. When I take the limit as n approaches infinity of that fraction, I get a 3. So I'm saying, okay, our series is essentially a common multiple or a constant multiple of 3 times a series that I know converges. So if you're a constant multiple of 3 times a series that converges, then you're also a series that converges. That is the logic of the limit comparison test. So you'd say, since the limiting value is 3, our series also converges. So I want to see some final statement here. So this series converges, and need to show the logic why, the limiting value 3 in this case. For number 9, I gave you a general term in there that had an exponential in it. So it has a geometric within it. I'm asking you to use the limit comparison test to determine the convergence of the summation from 4 to infinity of 15 over 2 to the n minus 9. So when I'm thinking of that, I'm thinking, well, I'm going to have to use a geometric series at some point, because that 2 to the n power, that exponential function in there, is going to generate a geometric series. So here's what I'm thinking. I know that the 15 part, well, I could always just multiply that to the outside. So the inside is essentially the same thing as 1 over 2 to the n minus 9, which is sort of the same thing as just 1 over 2 to the n. As n goes to infinity, 9 becomes inconsequentially small compared to the exponential function 2 to the n. So I'm thinking, okay, I'm going to compare this with the geometric series 1/2 to the n. And the reason I wrote it as 1/2 to the n instead of 1/2 to the n is it makes it more obvious that your common ratio is 1/2. And you say, well, why did you need to make that more obvious? Because we know geometric series always converge if that absolute value of your common ratio is less than 1. Well, 1/2 is less than 1. So this would be a convergent geometric series. Now, if I can show that the limit of the general term of the series that I'm trying to find out the convergence of divided by the general term of the series that I do know the convergence of, if I can show that's just some constant multiple, then it's the same answer. That's what I do here. So I take the limit as n approaches infinity of 15/2 to the n minus 9, and I divide that. Please notice, instead of writing it as 1/2 to the n, I said, well, that's the same thing as 1/2 to the n. In this format, it's better to write it like this. Means the same thing. But the reason that this is easier is now I can say, well, that 15, I can just factor out in front. And then I can say this is the same thing as multiplying by 2 to the n over 1, which means the 2 to the n goes in the numerator. This makes it easy to evaluate now because you say, well, as n goes to infinity, I'm going to have 15 times a fraction that goes to 1 because these two terms have the exact same value, and that minus 9 becomes inconsequential. Infinity minus 9 is still infinity. So I can say this fraction goes to 1. We're going to have 15 times a number approaching 1. The limiting value is going to be 15. Now, again, what that tells us is that since the limiting value is just a constant multiple, the convergence or divergence of our series is the same thing as the series we're comparing it to. I compared it with a convergent series. That means our series also converges. Pretty cool question there. All right, let's see. For our next one here. Ooh, beautiful. We're using the ratio test to determine the convergence of the sum from 1 to infinity of n to the 400th power divided by n factorial. All right. So now, if I think about this problem, I can say anytime I'm doing the ratio test, I'm going to go ahead and not even worry about the limit. I'm just going to think about what is the absolute value of that ratio of the a sub n plus first term divided by the a sub nth term. So in this case, what I do, and in this problem, there's no way that anything can be negative. So you'll see I just ignored the absolute value since nothing could be negative. And I said a sub n plus 1. That's going to be n plus 1 to the 400th power divided by n plus 1 factorial. Divided by a sub n, I just said, well, let's multiply by the reciprocal of a sub n. That puts an n factorial in the numerator and an n to the 400 in the denominator. Now, in simplifying these terms, I'll say, okay, let's put my 2 factorial terms in the first fraction. I have an n factorial, and my denominator, n plus 1 factorial, means n plus 1 times n factorial. That's going to allow me to cancel the n factorials in the next step. The other ones I just went ahead and put over here, the n plus 1 to the 400 over n to the 400. So now let's think about the limit as n approaches infinity of this ratio of a sub n plus 1 over a sub n. I can say, okay, the limit as n approaches infinity. My first term, where did this come from? I just said, well, n factorial and n factorial cancel, so I'll have 1 over n plus 1 here. Times, now I know that this is a limit as n is approaching infinity. So anytime I have a polynomial function, which both of these would be, I only care about the largest term. So I went ahead and said, well, yeah, this is going to be an n to the 400th plus 400 other terms. You'll have an n to the 399th power and n to the 398th power. I don't care about all of those because all of those are infinitely times smaller than that largest power. So I'll just say, I know that this is an n to the 400th plus ... doesn't matter. My denominator has an n to the 400th. Now, I didn't want to cancel those out just yet because I wanted to think about how do they interact with the other fraction. That other fraction is going to come over and multiply these. In the numerator, 1 times that just gives me the n to the 400. But in the denominator, I'm going to have an n times an n to the 400. It means my denominator is 1 power greater than my numerator. I'll have an n to the 400 divided by n to the 401. And anytime the degree of the denominator exceeds the degree of the numerator in a limit where the variable is going to infinity, that fraction goes to 0. So we say, okay, our limiting value is 0. What does that tell us? Well, the ratio test tells you that anytime the value of your common ratio limit as n approaches infinity of a sub n plus 1 over a sub n, anytime the value of that ratio is less than 1, then your series converges. Well, 0 is clearly less than 1, so I can say my limiting value is less than 1. 0 is less than 1. Therefore, this series converges. Done. Nice final answer. Now, the next two problems bring in power series, and they also are applications of the ratio test because in order to work a power series problem, you need to do the ratio test first step. So in a power series, you're going to have the variable x in with your series, and you need to find the values of x that cause the series to converge. So in this first one, in number 11, the first of the power series problems, I have the summation -1 to the n times x minus 5 to the n divided by 4 to the n times n. Okay, so I said, well, let's use the ratio test again. Just like I did in the last problem, I broke it down and I said the absolute value of a sub n plus 1 divided by a sub n. And in this problem, a sub n plus 1, you're going to have, since it's absolute value, I started to say you're going to have -1 to the n plus 1. That's completely irrelevant. And you think, why? Because it's an absolute value. So that just means you can completely ignore that. That's irrelevant. So I skipped over that term and I said, okay, first term is going to be x minus 5 to the n plus 1 divided by 4 to the n plus 1 times n plus 1. Now, you take that a sub n plus 1, divide it by a sub n. I choose to multiply it by the reciprocal of a sub n. So I get 4 to the n times n in the numerator and an x minus 5 to the n in the denominator. Now, I need to simplify out what's inside this absolute value. So I just say, well, what's the absolute value? I'm going to have 1 power greater of x minus 5 in the numerator. So I'll have a factor of x minus 5 in the numerator. X minus 5 cancels out of the denominator. I move on to the next term. I have 1 power greater of 4 in the denominator. So 4 to the n cancels out of the numerator, and I'll have a 4 to the first in the denominator. And then the n and the n plus 1 do not cancel at this point. So I have a factor of n in the numerator. I have a factor of n plus 1 in the denominator, and it does need a parenthesis around it. So I can say, okay, now I need to find out when this series converges. Well, I know it converges when the limit as n approaches infinity of the a sub n plus first over the a sub nth term is less than 1. I know it converges for those. So I already have what this a sub n plus 1 over a sub n simplifies to. Now I need to take the limit as n approaches infinity of that ratio. And I can say, well, as n approaches infinity, I know that this portion of it, n over n plus 1, remember what we were saying earlier, anytime the degree of the numerator and denominator is the same, you just take the fraction of the leading coefficient. So you say, well, it's 1 over 1. So I would think of this as the fraction x minus 5 over 4 times the limiting value of this is going to 1. So you say, well, that's x minus 5 over 4 times 1, which gives me just the x minus 5 over 4 inside of your absolute value. Now, again, the ratio test tells us that this would converge if what's inside of this is less than 1. That's what I put right here. Series converges when this absolute value of x minus 5 over 4 is less than 1. That means x minus 5 over 4 could be less than 1 or greater than a -1. So I have a 3-part inequality now. I multiply by 4 everywhere there. And I can say negative 4 needs to be less than x minus 5, which needs to be less than positive 4. We add a 5 everywhere, and you'll get 1 is less than x, which is less than 9. Now, we are guaranteed that the solution is at least between 1 and 9. That's what the ratio test tells us. But now, the ratio test is inconclusive whenever the value L is equal to 1. So you say, well, when x is 1 and when x is 9, my limiting value would be 1. So I need to test each of those endpoints. So and that's what I put right here. You will always have in the power series, you'll end up with an interval answer, then need to check your endpoints. So you'd say, okay, when x is 1, what happens? Literally plug a 1 in for x in your problem. You'll have negative 1 to the n times 1 minus 5 to the n divided by 4 to the n times n. So please notice, in the place of x, all I've done is I plugged a 1 in its place. Now, if I simplify, the group 1 minus 5 obviously is a negative 4. So I get negative 4 to the n for that second term in the numerator. Now, what I would do is I'd go ahead and just multiply my numerator bases together. Negative 1 to the n times negative 4 to the n, that's going to be 4 to the n. But then I notice, well, I've got a 4 to the n in the denominator as well. That cancels out, and I'm left with a summation of 1 over n. What do I know about the summation of 1 over n? You don't have to do any test. This is a divergent p-series in and of itself. This is the series called the harmonic series. Whenever p is 1, it's the divergent p-series. P equals 1, harmonic series. So I can say, well, what does that tell us? It diverges there. Then we're trying to look for the interval of convergence. At 1, it diverged, so 1x cannot equal 1. That's not going to be part of my solution set. So I'm going to say, all right, I know I had the right sign here. X must strictly be greater than 1. But does it have to be less than 9? Maybe not. I need to test. So if I let x equal 9, again, all I do is I plug a 9 in the place of x. And you can say, well, when I do that, that's going to make that second term positive 4 to the n. I'll have a negative 1 to the n times 4 to the n. This 4 to the n and the 4 to the n in the denominator cancel, and I would have negative 1 to the n over n. What do I know about this series? I know that this series, you could either use the alternating series test, also called the Leibniz test. That's what I called it here. And what does the Leibniz test tell us? It tells us if you can take the limit as n approaches infinity of the non-alternating part of this series, which is just 1 over n, is that limiting value 0? Sure it is. 1 over infinity would go to 0. Anytime that happens, this is conclusive evidence that this series converges. So you'd say, all right, if that series converges, that means that x equals 9 must be included in my convergence interval. The final answer for every power series has to look like this. You'll say the interval of convergence is, and it's always in terms of x. What's the lowest value of x? 1. And it cannot include 1 because we showed that it diverged when x was 1. But it can include 9 because the series converged at 9. So we say interval of convergence is the x values from 1 to 9, inclusive of 9, exclusive of 1. So parentheses around 1, bracket around 9. For the next of the interval of convergence problems, we're supposed to find the when the power series 5 to the n times x plus 4 to the n over 4n, what values of x is going to make this series converge? And so you'd say, well, in order to determine that, again, ratio test is going to be your best first bet. So I need to find the ratio of the a sub n plus first term over the a sub nth term. When I try to plug in a sub n plus 1, I would get 5 to the n plus 1 times x plus 4 to the n plus 1 divided by 4 times the group n plus 1. I multiply that by the reciprocal of a sub n, 4n in the numerator, 5 raised to the n power in the denominator times x plus 4 raised to the n power. So then I can say, well, there's a lot of cancellations that's going to occur here. If I look at the 5 to the n plus 1, I can say, Well, that can be written as 5 times 5 to the n. The 5 to the n will cancel with the 5 to the n in the denominator. The polynomial terms, I'll put in the next fraction, I have a 4n over 4 times the group n plus 1. Nothing simplifies there yet in this step. And then what about the binomial to a power? Well, the x plus 4 to the n plus 1 power means x plus 4 times x plus 4 to the n. The reason I write it like that is now I can cancel out the factor of x plus 4 to the n in the denominator. So when I take the limit as n approaches infinity of this a sub n plus 1 over a sub n, I'm taking the limit as n approaches infinity of, the first term here would just be a factor of 5. I'll leave the second term alone, the rational function where you have the polynomial divided by the polynomial, 4n over the group 4 times the group n plus 1. And then my last term is just going to be x plus 4. Well, remember here, the only thing going to infinity is the n. So the only thing impacted by the limit is my second fraction here of 4n divided by 4 times the group n plus 1. So you say, well, your rule there is anytime the degree of the numerator and denominator is the same, the limit as n approaches infinity is the same as the fraction of the leading coefficients. That's just 4 over 4, which is a factor of 1. So as I take the limit as n approaches infinity, this whole second term just becomes 1. So I have the absolute value of 5 times x plus 4 left after I take the limit as n approaches infinity. Now, once I do that, I need to go in and say, well, all right, the series is going to converge if this value of L is strictly less than 1. So I say, all right, the absolute value of 5 times x plus 4 has to be less than 1, which means negative 1 has to be less than 5 times x plus 4, which has to be less than 1. We divide by 5 everywhere. Negative 1/5 has to be less than x plus 4, which has to be less than 1/5. Now we subtract 4 everywhere. When I subtract 4, that's the same thing as subtracting 20 over 5. Negative 1 over 5 minus 20 over 5 gives me negative 21 over 5. 1/5 minus 20 over 5 gives me negative 19 over 5. So right now, I know this series converges if x is a value between negative 21 over 5 and negative 19 over 5. But what I don't know is, well, does it, I think I might have said diverge, converges if it's between there. But what I don't know is, well, does it converge at these endpoints? Don't know, have to test them. So the ratio test is inconclusive at the endpoints, so I'll have to test those endpoints. When I plug in negative 21 over 5, it gives me this in the original series. And I can see, okay, that's negative 21 over 5 plus 20 over 5 inside of this group. That's going to give me negative 1/5 to the n times the 5 to the n that I already had there. Well, anytime you have the same exponent, you can multiply those bases. So I can say 5 to the n times negative 1/5 to the n. That's the same thing as negative 1 to the n up there. And I can say, well, all right, that is going to generate an alternating series that I can use the alternating series test, otherwise called the Leibniz test, on. And I can say, since the limit as n approaches infinity of the non-alternating part, the 1 over 4n, since that part goes to 0, this series converges by the Leibniz test. So that means that x can equal that endpoint of negative 21 over 5. I test the other endpoint, negative 19 over 5. When I plug that in for the x value, my group becomes negative 19 over 5 plus 20 over 5. I'm going to have a positive 1/5 to the n power there. That positive 1/5 to the n gets multiplied by the 5 to the n. So, well, when I multiply those bases, that's going to give me just a base of 1 to the n. It doesn't matter what power 1 is raised to, 1 is always 1. So my summation just becomes 1 over 4n. And at that point, I just factored the 1/4 out so you could easily see, oh, that's just 1/4 times the divergent harmonic series where p is 1. If you have 1/4 times a series that diverges, your series still diverges. So we just say This is a divergent harmonic series or P series with P equals 1. What does that mean? It means that X cannot equal the endpoint of negative 19 over 5. Thus, my interval of convergence is the group beginning at negative 21 over 5 and including that with a bracket up to negative 19 over 5, and you have to exclude that with a parenthesis. And again, I'll always want to see interval of convergence is X equals low value to high value, and remember the brackets or parentheses around the endpoints.